Hey guys, welcome to my presentation on solving the buyer and seller's dilemma. This work is in collaboration with Professor Bhaskar and was done at the University of Southern California. All right, let's begin. So let me start by introducing what the dilemma is. Um, well, between buyers and sellers who are trying to trade a product for payment, there are two interactions involved. The first one is the delivery of the product, and the second one is the payment for the product. One of them is initiated by the seller and the other by the buyer. And hopefully these two are two separate transactions, but in a good system, they shouldn't be independent of each other. And of course, in the temporal sense, one of these two has to be the first one to occur. And depending on which one occurs first, there's two sources of trust that come into play. If the payment occurs first, then the buyer is trusting the seller to deliver its product after the payment. And the second alternative can be trust of payment, which is when the seller delivers the product first and then expects the buyer to be honest and make the payment. And we need a transaction system to settle disputes in case they arise. And so for any kind of dispute system, you need a disinterested third party, or maybe not. But in traditional systems, you need a disinterested third party. And the fundamental problem in that is the attributability of faults. And so if one of the actors is behaving maliciously, you should be able to attribute the fault to the malicious party and penalize them or punish them in some way. So let's look at an example in which buyers and sellers are at a dispute and we can't attribute faults. So let's say that the buyer says that let's say we are in a system where delivery happens first and then the buyer is expected to make payment. So after the first step, the buyer just says, hey, I didn't receive my product. And this is what a disinterested third party is seeing as a view of the system. It sees the buyer saying, hey, I haven't received my product. And this is after the timeout of delivery. And one thing that might have happened is the seller was actually malicious and didn't deliver the product. Or the second case can be that the buyer has actually received the product but doesn't want to pay, so it just claims that, hey, I just didn't receive my product. And these two faults make the same observations for a disinterested third party. And here lies the problem of inattributability of faults. So let's look at how this dilemma is solved by traditional systems. We usually have some sort of a third party arbiter or a dispute settlement system. And the three major types are legal systems where you enforce legal contracts, escrow services where you hire independent parties to act as arbiters, and the third one is reputation systems where you have public knowledge of what has happened in the past and behavior of actors in the past. These are like online retailer services, etc. So the first two are kind of have lots of things in common, which is they use a third party to attribute faults subjectively. So in case of legal systems, you use a jury to determine who was faulty subjectively and then attribute faults. And in escrow services, you hire independent arbiters and consultants to attribute faults to the players. And so the game looks like this. You have a buyer and a seller, and they can either play honest or faulty. And in case of legal systems and escrow services, if everyone's honest and there is no dispute, then the players get the payoffs that they deserve. If someone is faulty, then you may not be able to attribute faults because all you see is that there is a dispute and you have no other information at hand. And so the payoffs in case any one of them is faulty is very subjective and depends on how the dispute is settled. And so it's unknown what payoffs you'll get if you're playing faulty. Reputation systems kind of change the game. It's not a one-shot game anymore. it's kind of an iterated game where you see the games that a player has played in the past, and then you decide how you attribute faults. You can consider the example of online retail services, which operate in this manner. So, you existing systems definitely do rely on a disinterested third party to determine the outcome. And of course, whenever there is a disinterested third party, you're always susceptible to attacks of collusion and bribery. And the important part is that the cost of bribing or collusion is unknown to players before they start playing. And it's possible to bribe someone and get away with malicious behavior. So, in order to solve this, we propose a solution which does not require. So, we started looking for a solution which does not require a trusted third party. And blockchains were a natural choice because you can have a source of trust in the blockchain. And it basically is a dual deposit escrow contract, and it incentivizes both players to play honestly. And one of the major selling points of this protocol is that it places an explicit penalty on malicious behavior that players know before they start engaging in the game. So, with blockchains and smart contracts, there is an obvious problem of the smart contract actually being done. So it doesn't know what's happening in the real world. It doesn't know of any physical interaction or any kind of on-chain interaction. All it knows is the data and facts presented to it on-chain. And therefore, we can only provide incentives based on on-chain behavior. And we need to make manifestations of off-chain interaction into on-chain behavior. And by observing this, we can assign explicit payoffs and penalties for the behavior that you observe. And the great thing about this is you can place explicit penalties for malicious behavior, which is unlike existing systems. So the basic design philosophy is that for each step in the protocol, you make a provable footprint in the smart contract. So you break down the protocol into multiple steps. Each step is kind of atomic in its own way. And the result of that step is some kind of data that you put on the chain, you put in the smart contract that proves what happened in that step. And the objective is to maximize the attributability of faults. So any kind of faulty behavior in that particular step should be proven in the data that is retrieved from it. And if we do this, if we make more and more faults attributable, then malicious behavior is highly restricted because no one wants to be faulty and have everyone know that they are faulty. Okay, so let's look at some of the assumptions that we made. So we assume that the product is just some set of bits, maybe a digital key denoted by D. You can think of this as you're trying to sell data and you encrypt this data, the key is D, and you put this on IPFS. Another major assumption is that the buyer knows hash of the data, which is denoted by H of D. And buyer and seller have an asymmetric key pair, and their public keys are known, which is their addresses on the blockchain. And we don't consider transaction fees when we are doing our game theoretic analysis. Let's assume just that they are negligible compared to other amounts. So I'll just run through what the protocol looks like. Well, the first step is that a seller puts the hash of the data, a one-time nonce, and he stakes some amount, which we call the seller's deposit, into a smart contract. And the nonce is required to prevent replay attacks because we later verify some signatures. The second step is that the buyer stakes a payment and a buyer's deposit onto the smart contract. So at this point, the smart contract contains what the hash of the data should be, a one-time nonce, a deposit from the seller, the payment from the product for the product from the buyer, and a deposit from the buyer. The next step happens off-chain, which is the seller sending the buyer the data, and you send it in some specific format. So first, you append the nonce to the data, then you sign it with the seller signs it with its own keys, and then it encrypts it with the buyer's keys, so no one else can basically steal it, and it delivers this off chain to the buyer. And then if everything goes well, the buyer says, hey, I got the data, I accept that this was the data I wanted, and basically that's the end of the protocol. And the only pending step is then returning the seller's deposit to the seller and buyer's deposit to the buyer. And what we have at the end is the seller has parted with its product, delivered it to the buyer, everyone gets their deposit back, and the seller gets its payment, which is this step. Although a second thing might happen where the buyer says there's some dispute and I reject the delivery of this data. And as soon as that happens, the buyer has to provide some facts to the smart contract proving that something went wrong. So one of the possibilities is that the seller was malicious, in which ideally we should burn the stake of the seller and return the deposit to the buyer. The second thing that might happen is the figure B is the buyer was malicious and received the product and in bad faith just said that the seller was faulty. And in this case, it should be able to never prove that the seller was faulty. And its deposit should be burned and seller's deposit and the payment should go to the seller. But there is a third case that might happen due to some inattributable faults, which is both their deposits get burned. So this is an outline of the protocol from the paper. Let's not bother with this. And then we take this game, which is obviously a two-stage game where the seller plays first and then the buyer. And we analyze it with game theoretic tools. And we observe that the subgame perfect Nash equilibrium for this two-stage game is that both parties play honestly. So let's look at all the possible outcomes of this game. The first one is that the seller was malicious, but the buyer was honest. And the seller actually either sends the wrong data, but the data is signed and encrypted, or the seller sends some garbage strings. In the first case, where it sends the wrong data, the buyer can prove that the seller was malicious. So the buyer basically takes the signed data and nonce, provides it to the contract and says, hey, look, he signed this part, he signed the data and the nonce. The smart contract verifies that the nonce was right, then takes the data and hashes it. If it doesn't match the hash of the data, which the smart contract knows about, then you slash the seller. The second case is where the seller sends a garbage string or just goes offline. In this case, the buyer basically has nothing to say to the smart contract. And so this fault is actually inattributable because it might just be the buyer playing bad and just receiving the data but saying that it didn't receive anything. So this is an inattributable fault and both of them should be slashed. The second case is where the seller was honest but the buyer was malicious. The first one is that the buyer denies delivery of correct data, although it received correct data from the seller. And in this case, there is no piece of evidence that the buyer can provide to the smart contract, which makes it slash the seller, because you need a signed copy of the data and the nonce. And if the seller was honest, there's no way that the buyer can provide a signed copy of the wrong data with the correct nonce. And the last case is where the buyer says, I received a garbage string, which might just be the buyer, receiving the correct data, but saying that I received a garbage string. This is an inattributable fault because the seller might actually have sent a garbage string. And so both of them are basically slashed. And so the subgame perfect Nash equilibrium is both of them playing honestly after you do the game theoretic analysis. This being said, there is a bias in this incentive design where malicious senders are more disincentivized. What I mean is, in these four cases, the only case where faults are unattributable is when the seller is malicious and the buyer is honest. But this is good enough for the Nash equilibrium to exist when both of them play honest. So let's look at some of the limitations. The first obvious one is that the hash of the data needs to be public, but not the data. The data needs to be secret, otherwise the seller has nothing to sell. And this is a factor of trust because the buyer has to in some way trust that h of d is actually the hash of the data that it wants. Or maybe, I mean, I'm no expert in cryptography, but and it seems hard to exist, but there may just be some magic functions that keep D secret but let you know the hash of the data. But it's highly unlikely. And the second part is a griefing factor where um, the buyer or the seller can basically sacrifice their deposit to slash the other player's deposit. Now, this is important because um, it can lead to monopolies in the market where a seller with a large capital just goes out and buys stuff from its competitors, gets slashed itself, and slashes the other guys as well. And so this might just lead to oligopoly or monopoly. So some important discussion is needed. One question that's important is, why don't we just send all the data into the smart contract and just verify everything? Why do we need to do anything off chain? Well, the answer is that doing decryption on chain is very expensive. Um, it exists as a deterrent for malicious sellers, but this function is not expected to be used. Although it must exist because if something goes wrong, you actually need to do this. And the second point is, let's say I'm a buyer, and this protocol is requiring me to deposit more amount than the payment for the product. And so should the buyer be liable for something that's more than the payment for the product? And the answer, well, it seems like they shouldn't be, but we need it so that we make penalties for malicious behavior very explicit. And the same thing for the seller. If the seller is already selling a product, then why do you even need a deposit from the seller? Well, the answer for that is, again, let's make penalties explicit, and that the last step in the protocol requires some heavy computation, that is decryption. And well, if the seller was malicious, it should be on the hook for paying for all that computation. And this protocol can obviously be used to solve the problem of atomic swaps, because this is, in some sense, an incentivized atomic swap. Well, the swaps aren't guaranteed to be atomic, but the equilibrium is that both parties play honestly and swap things. And you can use this to swap data for payment, and it's an alternative to hash locks, although this protocol has much higher overhead. And you can also use this for physical products, where, for example, you lock something in a vault, which is opened by the key D, and then you trade these keys. This is very similar to the concept of like digital gold. All right. Thanks, and I'll be taking questions.
I have some question that is the dispute can also be distributable. So how can you guarantee that dispute, if someone like buyer or seller make a claim that there's some problem, and how can you prove that that is also obvious or not non-disputable?
Right. So this is basically the dispute settlement method, where you look at, so the buyer, the only person who can raise a dispute is the buyer. And if it received correct delivery, it can either just accept the delivery or raise a dispute. So if it receives correct delivery, but then raises the dispute, then there is no data that it can provide to the smart contract which says, hey, the seller was malicious and he should be slashed. Because what you need is a signed copy of the wrong data with the correct nonce, which an honest seller is never going to provide. So that's one of the case. And the second case is if the seller was malicious. And if the seller is malicious, then, well, it must either provide an encrypted and signed copy of the wrong data with the correct nonce, leading to it being slashed, or just some garbage strings, or maybe just nothing. in that case, it's an inattributable fault, and we have to slash both people. And then again, that's a limitation. That's a griefing factor where a person can sacrifice their own deposit to make sure that the counterparty also loses their deposit.
Can I have,
Hi. My question is, how is this protocol any different from BitHalo?
Well, as far as I know, BitHalo. Oops, sorry. Okay, so I think in BitHalo, all of the cases are unattributable faults, and both parties are slashed. But in this case, if the seller sends the wrong data, and well, the buyer is honest, then you can actually slash the seller. And this bias is good enough to make a Nash equilibrium exist, a strong Nash equilibrium exist.
Hi. Yeah, I might be misunderstanding, but at the early part of the slide, I think you mentioned that the hash of small d was made available to buyer.
Yes,
Yeah.
that's what I said.
Yeah.
Yep.
Here there.
So the assumption is that the buyer knows h of d, which is the hash of the data, but like obviously it can't know d, otherwise there is nothing to buy. And this is a limitation.
Yeah. So what I don't understand is like, if the buyer does not know what d is in advance, then what does knowing h of d help in this case? Because you
That's
don't
right.
know what d is.
That's right. So this is a factor of trust in the system where we need some sort of reputation system which provably tells you that, or maybe with high guarantee tells you that h of d is the data that you like actually want. It's like searching on a torrent where you search for a movie, you get the hash of the movie, you don't know whether it's the same movie, but well, you trust it anyway. And you can use some sort of reputation system to make this happen.
That means that seller, whatever data this guy is selling, will kind of enter some kind of dummy sequence or whatever it is to fit the h of d to become equal to what the buyer has. Am I understanding?
No, that's not what I mean. I mean, well, okay, you can think of it like this. In some sort of magical way, you know that, let's say you want to purchase a movie, and let's say the production house has made the hash of the movie file made known to the public, and you say that I want the data which maps to this hash, or just like ISO images for Linux distributions.
Oh, I see. So in this case, data is something everybody knows that is already there, but
Yes.
merely I don't have access to it yet.
Yes.
Oh, okay.
So you
Okay.
can think of it as a checksum.
Okay. Yeah, thank you.
Okay.
Hi, I might have misunderstood, but if I understand this correctly, the buyer's disincentivized to report the receipt of a garbage string, because if they accept it as the valid data, then they only lose the payment they gave. But if they report the garbage string, they lose payment and deposit, right?
Well, they lose payment even if they just go offline. So if you're a buyer and you receive a garbage string and you just don't respond to the smart contract, then basically both parties lose their deposit.
Sure. So in that case, if the seller sends a garbage string, the buyer would be better to pay for it than not, because
No.
then they lose just the money and not the deposit and the money that they paid.
So if a seller sends a garbage string to the buyer and the buyer reports it as a garbage string, you don't know whether the case is that the seller actually sent a garbage string or that the seller sent the correct data, but the buyer doesn't want to pay for it, so it says, hey, I received a garbage string instead. So it's an inattributable fault, and you don't know who's faulty. And so, well, the obvious choice is just slash both of them. So they both lose something, but in like the global overview, the Nash equilibrium remains that both parties remain honest.
Okay, I think that makes sense, yeah. But so if you, just so I'm clear, if you did have a malicious seller sending a garbage string and an honest buyer, they couldn't report this because they would lose more.
No, they would report it. I mean, it doesn't matter if they report it or not, because in any case, they both lose money. They both lose their deposits.
Is that guaranteed? Could the buyer just accept the garbage string as real and pay for it?
I mean, they could, but yeah, it's basically the same thing across the board. Either you report that you received a garbage string, or you just go offline. But if you accept delivery, then you don't have to prove anything to the smart contract. If you just say, I accept my delivery and there is no dispute, and give the payment to the seller.
Okay, and in that case, the buyer would
Yeah,
not
but in
lose the
that case,
deposit.
it would receive its deposit back.
Okay, that makes
Right.
sense. Thank you.
Due to the rush, I forgot to introduce this speaker, actually. He's a recent graduate with interest in consensus mechanism and crypto economics, and he's working also for the implementation of the SCBC Casper protocol for Ethereum behind the foundation. Okay, so having said that, we're moving to the next talk by Matthias Grandmann, who's a PhD student at Karlsruhe Institute of Technology in Germany. He has worked on monitoring the network layer of Bitcoin protocol and currently working on improving and exploring second layer solutions that help scale the Bitcoin technology.
Thank you. This talk is about BANKLAVES, a concept for a trustworthy decentralized payment service for Bitcoin. My name is Matthias Grundmann, and this is joint work with Mark Leinweber and my PhD advisor, Hannes Hartenstein. Let me start by putting BANKLAVES into the context of second layer architectures. As a second layer architecture, I refer to an architecture that is above the blockchain as the first layer, and you can deposit coins into the second layer by locking them on the blockchain, and then you can perform internal transactions inside the second layer and perform a cash out, making the coins available again on the blockchain. There have different approaches been presented for such second layer architectures. For example, sidechains, which is basically a blockchain that is connected to a main chain, and you can have multiple of such sidechains. Depending on their consensus algorithms, there are quite different approaches for sidechains. You need to require trust into the majority of miners, which is one disadvantage of them. You could also implement the second layer architecture using smart contracts, which just keep managing the balances of the users. However, if you use smart contracts on a public blockchain, those cannot hide the transaction history. You can also think of payment services or wallet providers or Bitcoin exchanges as a second layer architecture, because you can also deposit coins, perform internal transactions, and do a cash out. However, those exchanges require trust into a central instance. And the past has shown that such trust is not always a good idea, because those services vanish or are hacked and users lose their coins. And probably the most famous second layer architecture are payment channel networks. We've heard yesterday about the Lightning Network. It is a very great idea. However, the problem in payment channel networks is that valid routes have to exist between a sender and the receiver of a payment, and there needs to be enough available balance on one route. In our work, we want to explore what advantages and disadvantages trusted execution environments give us. So we see in all of these different approaches, they have their advantages. All are great ideas, although only one disadvantage is shown on the slide. But all implement a trade-off between some challenges and opportunities they present. And we want to look at what trusted execution environments give us and what trade-off we can get. Maybe you already know second layer architecture using trusted execution environments. This is T-Chain. And we would put T-Chain in our picture here because, T-Chain implements a payment channel network. So it is especially a payment channel network. And what we are looking at is a more generic approach that we don't want to implement a second layer, a payment channel network, but a more general second layer architecture. And BANKLAVES is more influenced from thinking as a payment service. So what are the goals for our BANKLAVES approach? We want to have the payment service operations to deposit coins, perform internal transactions, and withdraw coins. We want a decentralized approach, so we don't want to trust a central party. We want the users to be able to cash out at any time without depending on the cooperation of another user. And to be realistic, we want users to be able to go offline, so they don't need to run their computer running the BANKLAVES system all the time, and they can disconnect from the network if they use it on a mobile phone, for example. And we want that users can perform backups, because if a user's computer crashes, they should be able to restore from a backup their state so that they can still have access to their coins. And what we use are trusted execution environments, short TEs. Those are established by trustworthy features in hardware and software. And the features we require are isolated execution, meaning that the code is run inside an enclave, which is a protected area inside the CPU. And neither another application nor the operating system has access to the code run in this enclave. So we also have protected memory, which means also the data that is processed inside the enclave is protected from the operating system. And when the data leaves the enclave, it is only stored in the main memory in encrypted form. And we also need remote attestation, which means we can remotely verify that some specific code is being run in an enclave. And we can verify that the platform is not manipulated and it is a real trusted execution environment. Those features are implemented, for example, by SGX. However, we assume an ideal TE, which means we assume a bug-free implementation just of a model TE. In TEs, you have the effect that if you want to make backups, you have to provide a function that stores the state of a TE in encrypted form. And if you are able to store state, you can also revert an old state of the TE, which is called a rollback attack. And this is a problem that we need to be aware of. But first, let's look at how our system is built up. So at a user, we have each user runs an enclave on his computer and a Bitcoin client, which is shown here. And the same setup, the same application runs on each user's host participating in the system. All the enclaves are connected through secure, encrypted, authenticated channels from one enclave to the other. And the Bitcoin clients are connected to the Bitcoin network. And this network of enclaves forms our enclave network, which is our second layer architecture. So let's look how the basic operations of a payment service work in our system. So if Alice starts a new network, she starts the application on her computer. And if Bob also starts the application, they can connect to each other, and both enclaves perform a mutual remote attestation, which verify that they both are running the correct code. They connect their Bitcoin clients to the network. And now Alice can perform a deposit by telling her enclave to create a new deposit address, which means the enclave creates a private-public key pair and creates a Bitcoin address that Alice can create a transaction to. So Alice, for example, sends 5 Bitcoins using a blockchain transaction to this address that the enclave has provided. When the enclave has confirmed that the transaction is part of a confirmed block, the enclave updates its state, meaning the enclave keeps track of all balances of all users, and this state is also sent to Bob's enclave. The secret key required to send the bitcoins from this deposit transaction to another address is also sent to Bob's enclave. However, it is secure because the key is only kept inside the enclave, inside the trusted execution environment, which means Bob cannot access this private key. It is protected by the enclave. Now, it is quite simple to do an internal transaction. If Alice wants to send 2 bitcoins to Bob, she can just tell her enclave, and the enclave updates the state and sends the new state to Bob. And by the time Bob's enclave sees the new state, Bob knows that the transaction has happened. And in this case, both users, Alice and Bob, can perform a cash out without being dependent on the other party because both enclaves have the secret key required to access the funds. Let's look at a first problem. We have the rollback attack, as already mentioned. And now, after the transaction, Alice could do a rollback to the state before, when she had 5 bitcoins. And now Alice could use those 5 bitcoins to perform a double spend by performing an internal transaction to another person, say Charlie in the network. So we need somehow to make those rollbacks not possible anymore. And Intel SGX, for example, offers hardware monotonic counters. However, those are impractical because they're slow and they can run out. So we don't use a TE feature to handle this, but we handle this on the protocol level. So what we do is we introduce one leader enclave, which is guaranteed to have the most current state. And this leader enclave verifies each internal transaction that the participating users use their most current state. I'll come back to this later, but first we look at another rollback attack because let's go back to the state where Alice has performed the transaction to Bob. And now Alice again performs a rollback to the state where she had 5 bitcoins. And now Alice does not perform an internal transaction, but performs a cash out. And to prevent a cash out in this case, we could either, again, use a leader to verify that the cash out is possible, to verify that Alice has the most current state. But this would require cooperation of another user, and we want Alice to be able to access her coins immediately without cooperation of another user. And for this, we borrow a method that is known from payment channel networks, meaning we allow the cash out from Alice's transaction, from Alice's enclave, but this transaction is time locked, meaning the transaction does not become valid immediately, but only after a specific amount of time, for example, 24 hours. And during this time, the other enclaves in the network have to verify the cash out transactions they see on the blockchain and verify that the cash out transactions are valid. If they are not, so for example, in this case, if Alice cashed out 5 bitcoins, although she only owns 3 bitcoins, Bob's enclave can create a breach remedy transaction, which becomes immediately valid, and this transaction moves the coins back to the enclave, to an address that is owned by the enclave. And because this transaction becomes immediately valid, it renders Alice's transaction invalid. However, we have a problem here, because let's look at the state again when Alice performed a transaction to Bob. Now let's say there is another person in the network, like Charlie, who sends 2 bitcoins to Alice. If she performs a cash out now, it is the same situation from Bob's point of view. So Alice has created a 5 bitcoin cash out transaction, and from Bob's point of view, she only owns 3 bitcoins. So now we have to distinguish those 2 situations, because in this scenario, the cash out transaction should be valid. And what we use here is mechanism that we called Satoshi bookkeeping. We introduced Satoshi is the smallest unit of a Bitcoin, and this mechanism keeps track of the ownerships of all of the Bitcoins after all transactions. So this is a sum of the results of all transactions that have happened. Let me show you an example of this. Let's look at the situation after Alice deposited 5 Bitcoins. So now the enclave has stored a balance of 5 Bitcoins for Alice, and the enclave has access to one UTXO, one unspent transaction output that is owned by Alice over 5 Bitcoins. Now, if Alice performs a transaction of 2 Bitcoins to Bob, she would, on the blockchain, create a transaction that spans this 5 Bitcoin UTXO and creates 2 new UTXOs. One that spans 2 Bitcoins to an address owned by Bob, and one UTXO that is owned by Alice, the change output over 3 Bitcoins. And in our mechanism, in the Satoshi bookkeeping, we mimic this blockchain behavior by saying that we keep the same UTXO, but the enclave stores that one part, like the first part, is owned by Alice using 3 Bitcoins, and the second part is owned by Alice over 2 Bitcoins. So this mimics the creation of 2 new UTXO by using the same UTXO and just storing which part is owned by whom. And now Bob's enclave can verify that if Alice creates a cash out transaction, she includes like which part of the UTXO she spends, and Bob's enclave verifies that she only spends the part of a UTXO that is owned by Alice, or at least not by Bob. If Bob sees that someone spends his UTXO, then his enclave would be able to create a breach remedy transaction. So to sum up our key concepts, we have introduced the leader as one of our components, which is an enclave that is always guaranteed to have the most current state. And this is guaranteed by intermediating every internal transaction. So the leader enclave is always notified of an internal transaction, and the leader enclave can, in this way, prevent a rollback by verifying every internal transaction. However, the leader is not one dedicated user that runs the leader enclave, but it's just one enclave in a network that is guaranteed to have the most current state. We also introduced emergency cash out, which makes it possible that a user can cash out, can create a cash out transaction without cooperation of another enclave. And we introduced Satoshi bookkeeping, which makes it possible that it is always guaranteed that those emergency cash out transactions and the breach remedy transactions are created correctly. So now let's review of the goals we had, what we reached. We wanted to implement the payment service operations, which do work. We wanted a decentralized approach, which is a bit not decentralized because we have a leader enclave. However, I would argue it is still decentralized because each enclave can become a new leader, so we don't have this dedicated host. And you don't even have to trust the user running the leader enclave because the leader enclave is in a trusted execution environment and the user cannot manipulate the behavior of this enclave. We wanted that users can cash out at any time. This has a little drawback because they can cash out immediately by contacting the leader and having their cash out verified, or they can cash out without cooperation of the leader, but then the transaction is time locked, so they need to wait for a moment. We wanted that users can go offline, which is generally possible. They can always access their funds even if they're offline or not connected to other enclaves in the network. However, users need to be online to receive internal transactions. This is because users have to get notified of their new state, so they need to be connected to the network. And if the leader crashes and there is no leader in the network, then we require all enclaves to be online to elect a new leader, because we need to guarantee that only the enclave with the most current state can become a new leader. And we wanted users to be able to perform backups, which is possible because we handle the rollback attacks, which are enabled by allowing users to restore backups. There's a caution you have to take. The BANKLAVES approach, as presented here, relies heavily on the security of TEs because we store the secret keys on every enclave. So you cannot, you have to really trust the TE, and concrete implementations of TEs have shown to be compromisable. So let's sum it up. We have seen that TEs allow for a relatively simple second layer architecture because you trust the TEs and you know that the code which is run at other users' hosts is the correct code that you expect those users to run. And you can store data at other users' hosts, even like secrets you don't want those users to be able to read, and those are protected by the TEs. We've seen that rollback attacks are still possible, although we use TEs, but we have presented concepts that handle those rollbacks and assure that they are not a problem. And in our paper, we have a proof that it is always possible to create a correct emergency cache out, and only if a user cheated, then it is possible to create a breach remedy transaction. A future work for us would be to analyze how we could handle broken TEs. If one user, for example, is able to compromise the TE on his host, and we want to perform a performance analysis using Intel SGX and introduce transaction fees and see how we can incentivize users. With this, I want to thank you for your attention, and I'm happy to take questions.
Hi, thanks for the talk. So during the remote attestation, you have to actually ask Intel, right, if the remote enclave is correct or not. So you have a centralized trusted party. But I mean, this is a SGX.
Yeah.
So is it possible to, like even theoretically, to have a remote attestation without this trusted party telling you if this enclave is correct or not?
As far as I know, this should be possible. So Intel could publish the public key or any other party which is necessary to verify that one attestation is correct.
Okay, so because now Intel just provides you the public key of the private key that they put inside the enclave, right? Or
I think they just provide the public key that you need to verify that one verified attestation by one reply of the Intel attestation service is correct, but you cannot verify a measurement by the enclave itself. So this needs to be verified by Intel.
Okay. And the second question, are you aware of T-Chan, which is also doing this payment channels using SGX?
Yeah, that's T-Chain.
Yeah, what's the main delta between your solution and...
Yeah, T-Chain implements a payment channel network, which is especially a payment channel network and has thus the drawbacks of payment channel networks and the advantages. This solution is more like a payment service in contrast to a payment channel network.
Okay.
So it's related, but...
Okay, thank you.
So, could you replace the trusted execution environments with homomorphic encryption if that became more efficient at some point?
I would have to think about it, but thanks.
I have one question about trust environment. So you are using running some operation on a trust execution environment, and why there's possible to have a rollback. So you are allowing general purpose operation on trust environment, or in my opinion, it's better to have a special purpose operations that we do not allow any kind of rollback operation. Then there should be no problem of rollback attacks.
Yeah, that's true. So in general, you don't have this problem of TEs because like the memory is, there is a freshness guarantee, so you cannot take a snapshot of a running TE and restore that. However, we want to enable users to perform backups. So we need some way that they can store a state. If the computer crashes, they can restore the state. And then we introduce ourselves the problem of rollback attacks.
Yeah, I have a question about what if the leader, if the elected leader fails to conduct its duty and somehow publishes the stale balance, and if the cash out is made with that stale balance, then how will that be taken care of if the damage is already done? It's kind of a, because I'm not that familiar with the T's, so it sounds like as long as we can guarantee the accuracy of T, then that T will somehow function like a Deus Ex machine or something like this. Because I don't know, I don't have that much knowledge about T. So, yeah, could you answer that question?
I'm not sure if I understand you correctly. So it is guaranteed from the assumption of the TE that the leader enclave can only do what the application allows. So it is always guaranteed from the protocol that it has the most current state, and therefore it cannot publish a transaction with an outdated state. Does that answer your question?
Okay, yeah.
So the next presenter is Nelson Bohr, who's a research engineer at IBM Research in Africa, a member of the Industries Research Group focusing on the intersection of blockchain and artificial intelligence, applied to the areas of healthcare, finance, agriculture, education, among others. His research interests lie in the following fields: distributed systems, Internet of Things, blockchain systems, and edge computing. He holds a bachelor's in software engineering from University of Eastern Africa at Kenya, and a master's from Georgia Tech in Atlanta, in the United States.
Good afternoon. I'm Nelson Kibichi Bora. I'm going to take you through a scalable blockchain approach for trusted computation and verifiable simulations in multi-party collaborations. Computational decision-making in large-scale experiments require sensitive policy-level decision-making. And so decision results from these simulations can be from different independent agents. And so in this case, computational validity at times might be tricky, and it might not even be guaranteed. And some of the epidemiological simulations that we've worked with is eMod, Neuron, and DNN training. So we've just worked with open malaria with the experts on the other domains as well. So one of the examples of the eMod that I've just talked about is shown here, whereby a malaria data scientist runs a given scenario. And in this case, their goal is to alter different interventions, either vaccines or nets or many other, and they alter the demographics, the entomology, the health systems, and then the model. So their goal is to really evaluate and can get to a number of 500 policies to be evaluated, and they make a decision based on those interventions. So in this case, it's a perfect use case that needs a trusted output from those policy-level decisions. And so looking at the untrusted computing agents, we can see that, for instance, open malaria, you can take a couple of days to simulate the 500 policies, like 3 or 4 days to make that decision. So the fact that it takes a longer time and also needs a lot of expensive computation, so it's also a tricky area to consider. Then also computing agents may have their own vested interest or lack of computing resources, as thereof mentioned, and also you can imagine running a simulation for days, and if it gets into an error, or rather if you don't evaluate rightly, so that is also detrimental because you're dealing with healthcare. And so it can be really challenging in terms of scaling. At the moment, really, what they're doing is the scientists on the ground run the simulations and they just decide, do I trust this or this based on the experience? So if you're more experienced, you can be trusted to choose. The other example they do is they do random sampling. So they just pick on one. It helps them for sanity checks that they've done a validation, but also it's not it's limited in terms of probabilistic validation, and all these options also it has to be inferred by a policy agent. So it's really not transferable to another simulation thereof if need be. Our trust requirement that we're looking at is, one is we should be able to trace the source of decisions and errors therein, because remember our first assumption is it's healthcare, so it's very sensitive in whatever you're going to decide. And then can we prove, or rather can we hold them in the decision they're going to make over time? Then can it be reliable in the sense that it's an open trace or guarantee also to the people making the decisions? And so we have two stages of trust, in the sense that one, we are saying, can we validate, can we guarantee consistent steps of computation which can be agreed upon as being correct over time or a given period of simulation? And also, can we verify those computational consistency through any given simple check? So these two are what we're building upon as the trust elements of computation, especially now in this domain of healthcare. And so distributed trust for this computational framework, one, we need to be able to validate the computation of the transaction. And two, we also need to be able to the consensus in terms of the validations among the agents. So if I've run a given simulation, we need to agree, all of us, that this is agreed upon as being correct. And again, I keep emphasizing on this aspect that it's healthcare, so it has to be really critical in that point. And also, it has to be shared to others as well, so that it can be transferred. Remember that point I said it has to be transferred from other to learn from their decision. And also the fact that it's the computational integrity, maybe using a given simple checks. This really defined blockchains, and that's why it was really a perfect solution to address their need. Further on, looking at the cryptographic validation, which needs that aspect of validating the output from the machine learning models. We have the several approaches, which is zero knowledge proof. We also have the probabilistic checkable proof, and also one can generate cryptographic trace of computation, which can be used to really check by a doubting peer. The challenge with those as well is it increases computational effort at the end of this client. Remember, we said it takes like a couple of days to complete, and also the implementation can be a challenge as well. And so what we did is looked into using an iterative simulation model, whereby the system is defined by a state at iteration t, that's give you state xt, which is a real vector. Then it evolves as a function of current state and external randomness. And then the validation of state means that the reported state x tilde t is close to the recomputed state x at. That is, the client reports the state x tilde t plus 1. So if we recompute it based on an x tilde t to get x at t plus 1, then they should be close. And we have a validation tolerance, which the smaller the delta, the stricter the requirements, depending on a given use case. So we also have a computation-based validation model, whereby a client performs the computations based on the original iterations and reports the computed states to the endorsers. Then the different frames have different disjoint set of states and are validated by disjoint sets of endorsers in parallel. So the endorsers in this case validate frames and send the endorsement send the endorsements of the frames to the orderer. Thereby the orderer then performs what it does, which is checks the consensus and appends the frame to the ledger. And in this case also, it's good to note that since the frames are validated in parallel, each endorser performs a fraction of the computations, which helps in handling the heterogeneity in communication and computation delays, which can be better handled. So that's the computation-based validation model. And so now that we've introduced, looking at our picture earlier on, we've introduced a third one, which is a simulation parallel validation. And in this case, it allows us to validate, it allows us to do validation of individual states or by endorsers sets. and also the ability to store on blockchain, which enables us also to do verification by checking the chain consistency. Also, the trust guarantees are transferable really here in this case of blockchain through the ledger. But again, having introduced these simulation parallel validations of the different states, we also encountered a challenge of large overheads of communication and storage. And to look into that, we considered using 4 main tools. One was delta encoding, whereby the iterative computation successive states mostly close to each other. We don't really have to store each of those states. We just store only report changes in those states so that it reduces on the storage. We also did a lattice vector quantization where we report only the approximate version of the states. And in this case, we quantize the different state differences using lattice vector quantization. We also did the successive refinement whereby a reported states might have compression errors if leading to invalidation, in this case, if it's compressed too costly. So in this case, we allow the client to refine the communicated estimates by using the successive also refinement lattice vector quantization. Also, we considered using the subsampling, which is that the orderer can sample and store only important states in the chain. And also, we considered using the coded computing to reduce validation overheads. One is just using peer independence to parallelize the validation process, and also help us to avoid waiting for too long for stragglers and account for the presence of adversarial endorsers if there are. So further possible really additions in this case is we can also look at task assignments to endorsers can be optimized based on communication and the computation cost. So an example of the compression schema we have is a group of iterates is grouped into one frame, and then the first state in the frame is using the dictionary-based compressor lossy-lempev, then compute the state changes in the successive states using the delta encoding starting from the first state in the frame. Also, we did the compression of the state updates now using successive refinement lattice vector quantization. So this is just an example of how we group frames together. Further on, we can now see the overall system model, whereby a client then is able to compute, and then after computing, then they are able to compress and then send to the endorser. The endorser then should be able to validate by recomputing that and sends the endorsements to the orderer. The orderer then proceeds to check the consistency and subsamples and stores to the blockchain ledger. Now we have the full validation compression framework, which provides the validation and the verification from before and reduces the overheads. Also at the expense of more computational blocks. So we just introduced a multi-agent now blockchain framework, which helps us to validate the given outputs of a given machine learning or a model in this case. And so the advantage really, it's distributed, scalable, and we've proved that we can reduce the aspect of communication and storage challenge that we had. And so looking at the experiment, we had a computational system where we train a 3-layer neural network using SGD on MNIST. And so the client is computationally limited in this case and can only sample small batch sizes and is limited number of iterations of SGD. So other endorsers have more computing power, but only have access to limited training data. So in this case, they can only train the network independently. And so here, the stages are the weights of a neural network, and the validation threshold is chosen to decay with a number of iterations. So the closer convergence of SGD, the stronger the requirements for validation, and so the more accurate of the reporting of the neural network weights. And so looking at the cost of trust that we had, the best case that we had is using small compression errors, and then we have the moderate frame sizes. We have also the cause case, which allows for larger compression error for the same frame sizes. We also have a larger frame case, which really looks into the fine compression or small compression errors, but larger frames. And so we can see the communication chart on the here we can see that the communication increases with a decreasing validation tolerance values as clients have to send more accurate representation of those states that have been invalidated. Also, we can see that the communication cost is really minimum when we compress costly as each state takes fewer takes fewer bits to communicate. Also, to note on the communication cost, we can see that when you use a larger frame, it also marginally reduces the communication cost, and thereby because at that point there are fewer frames and so fewer checkpoints, and so at that point when there are fewer checkpoints, it's so lesser bits to be sent. Looking at the computation cost, we can note that computation cost is more when there are more invalidations. Really, in this case, states have to recompute more times by the client and the endorsers when the reports are invalidated. And really, it's also due to, we can see also when the validation tolerance is low, we have the, when validation tolerance, or rather computation cost increases with the decreasing validation tolerance due to more likely reports of invalidation. And so in the computation cost as well, we can see that using cause compression, the red line increases approximation error in state reports. And so more states are invalidated at that point. And so that's the endorsers and clients have to reevaluate the states more times. When using also long frames for the recomputation cost, it ends up communicating more iterations at once because it's a long frame. But again, if a state in that frame is invalidated, the client has to recompute all the states starting from that point. So larger frames can incur also more recomputation by clients, especially if it gets into an error within a given frame. Looking at the precision improvement, whereby we remove spurious gradients to assist in learning. So since endorsers check if the neural network weight updates do not deviate from the mean change, which is what a vanilla GD uses. So the validation mechanism eliminates spurious gradients. And so only good gradients are used in this case more often. So even though client uses small mini batches of 10, of size 10 samples, note that the precision of the resulting network is much better than SGD with 10 sample batches. So further, the stricter the validation requirement, better the performance of the validated models, as endorsers in this case allow far better gradients. We can also note that the precision is almost as good as using batches of size 50 and consistently better than using 30 sample batches. And so in this case, we can conclude that the validation helps to eliminate spurious gradients, and thus gets more out of each iteration. And so in discussion and possible extension, we've proven that we have a trust framework which eliminates spurious computations, and also we have a validation process which helps to establish trust in steps of computation. Then we can also have an audit record which can be audited over a given period of time, and also the compression, the validation protocol which reduces overhead. Some of the possible extension that we are looking at is customized adaptive compression mechanism that can be able to learn from computational processes. And in this case, really, can we then make one model learn from another model, and thereby helps when you're running a model, it doesn't start from scratch, but it can pick up from where a given model I had left it out. And this is very critical in the disease modeling community because of the long periods of times that they have to run. So that's all. Any questions?
First of all, we're still running on time, so we do have time for questions.
You'd mentioned at some point that you also looked at coded computing to deal with stragglers and adversarial settings. Is that following some of the work from Avistamir?
Yes, we have some other work looking into adversarial that I'll share tomorrow. Okay. So we basically took this framework and now applied it in a practical open malaria simulation. And so in that case, you have to look at what if an agent says, or rather reports wrong reports. So how do we then identify that? So that's what we looked, and I can share more on that as well. Yeah. If you have any question, we can really. Oh, okay.
Why are you using what?
I think just because of the expertise in the team and the availability to prove the platform, in the sense that can we detect in terms of the computation based on the framework. You remember the framework that I gave you have to group iterates, and so some of this is just the knowledge base, and so the best example that I can give is what I've just showed, in the sense that we took the same framework outside of MNIST and now applied into a real machine learning model for healthcare. So this is just for demonstrating the capability of the platform, but now we took this now and applied into a real world setting, but I can share more details on that as well. Yeah. Okay.